with chapter number 15 of the reverse engineering course. During the reading part, we talked about multi-thread applications, why multiple threads can be very useful for performance enhancements, and we also discussed about the common APIs that are used in the Windows operating system in order to create a new thread or to synchronize multiple threads with each other. So in this video we are going to deal with an application that executes code via different threads and not just one main thread as we have seen till this point. So let's start by running the application. We see that it asks for a password. Let's write something, just press enter. We didn't expect something different, so let's try now to do something else. I'm going to run the debugger only and then run the application. Let's see what happens. We see that it starts and very soon then it's going to terminate itself. So we can understand that it implements some kind of specific reversing tool detection, since the application is not debugged, but it still can detect only debugger. It seems that it has some kind of trick that targets only debugger itself. It tries to detect if only debugger is running. So let's do something that we haven't done till this point. We're going to run first the application, and while the application is waiting for our input, we're going to run only debugger, and we see that the application was terminated. Let's try to do this again. We have the application here, run only, the application terminates itself. So this can make us think about different threads. Since the main thread is waiting for our input, it makes sense that there must be another thread that is active at the same point, and where code is executed and checks for presence of a running instance of only debugger. So let's start analyzing the application. And let's search for all intermodular calls to see if we can locate a call to one of those known APIs used in Windows to create a new thread, as we saw during the reading part. So let's start typing create thread. We see we don't find. Let's sort it by name. We see that we cannot find the call to create thread. Let's press Ctrl+A to analyze the entire module and do a scan again. Search for all intermodular calls. Start typing create, and we see here two calls to create thread. So as you can see, the compiler chose to assemble the code in this way. So it moves to the address of create thread to ESI and then calls that API through the register. That's why before analyzing the module, the debugger couldn't understand that this call to that specific register resolves to a specific function and a valid address. Okay, so what we can do is to place a breakpoint here and another one here, and now we are ready to execute and see what really happens. Before proceeding, just keep always in mind that instead of searching for intermodular calls in order to locate a call to a specific API, you can always go directly to that function if it is located in one of the loaded modules, and directly place a breakpoint there. So whenever this API is called, you're going to break. This is very useful because sometimes, as we saw in this case, a function or an API might be called not directly, but through a register or through an indirect memory reference. So you might not be able to see the call to that API, even because the address can be dynamically calculated on runtime. So if you suspect that an application makes a call to a specific API, you can go directly to that API and place a breakpoint there. So at this point we have these two breakpoints that we placed earlier. And let's run and see how the new threads are created and what is their purpose. So I'm going to just run, and we see that we break at the first breakpoint to the create thread. Let's take a look at the parameters. We see that the entry point of the function that is going to be executed in the new thread starts at this address here. So we can right click and follow in this assembler. We can set the breakpoint here. And we also see that another thread is going to be created after the first one, of which the entry point of the function that is going to run in the new thread, it is located here, so we can follow immediate constant and also set a breakpoint here. We also see that after the creation of the second thread, there is a call to the wait for single object API. And we also see that the object is placed in EX. When we call create thread, the handle of the object, the handle that represents that object, is placed in EX. So create thread returns the number of the handle in EX, and then as you can see here, it pushes EX and then waits basically for that thread to finish its execution before the main thread can continue execution. But you can notice that for the first thread, the application doesn't wait, so it just calls create thread. It doesn't care if the new thread is going to actually start immediately or after a few milliseconds or after a second. It doesn't really care. The main thread will continue its execution and will create another thread, but then it's going to wait for the second thread to finish. Okay, so let's just run with F9. And we see that the application was terminated. So let's run this again. We see that the application kills itself. and the only debugger didn't correctly handle the software breakpoint. So let me run again. I'm going to start stepping over instead of running. We see now that we managed to break in the entry point of this thread. All the debuggers should have been able to break in the first place. There might be some problem also with the virtual machine I'm using, even though I don't see any reason why this should affect a software breakpoint. So let me try to do this again. We have our breakpoints here. And let me also put a breakpoint further down this code that's going to be executed in the other thread. Let's just run and press F9 again. Okay, it seems that now the breakpoints work. So let's start executing instruction by instruction. We see that the application here calls the isDebugger present API. We see that at this point we have two threads running, active. So it returns 1, it means that it detected the debugger. So if it did, it's going to call EDI. You see that in EDI there is the address of the get current process. Then it's called ESI, and that you see that in ESI it's placed the address of terminate process, so it's going to kill itself. So let's go one instruction back, set EX to 0, and start stepping over again to bypass this trick. And then we see that it calls find the window A through the call EBX. You see that the address of find the window A is placed in EBX. So it tries to, if you step in with F7, you see that it tries to locate all the debugger through the class name of its top level window and checks if that was successful. If EX is not 0, this means that it detected. So let's turn this to 0. And what we see is that it's going to sleep for 1 second and then it's going to jump up. So it's going to run for all the time the application is executed. This thread constantly runs, checking for only debugger through the find window API, and for a generic ring 3 debugger through the isDebugger present API. We can either patch these two APIs internally to always return 0, or we can modify the process environment block as we have seen in the previous videos to disable the isDebugger present API, or we can just patch the code so that these jumps are always effective, so the application will never terminate itself. So let's just press F9 to continue executing, and we see now that we stopped in the next thread. So we see that when trying to step over this function here, let's try to minimize this window. Okay, so let's try and enter a password of our choice and see how the application is going to validate it. I'm going to place also a breakpoint here. Just enter code, press enter, and we see that it checks if the length of the code we entered, which is 5, is equal to 14 hex, or in other words 20 characters long. So we now at least now we know what the correct length should be, and we can restart the whole process. But before doing so, we can go and copy the modifications we did, so that we don't have to deal with anti-reversing tricks anymore. So let's start again. We have the breakpoint here. Let's run. We can remove this breakpoint from here and here. This is going to, as we see here, it calls the wait for single object, as we said before. So let's press a breakpoint here. Just run. So we stopped at the other thread. You see you have 3 threads active, the main thread and 2 other threads. Okay. And you see, for example, this is the stack of the current thread under execution. You see this is the base address. So if you go on the memory map window, and search for that specific address, let's see, this is A6D, 3 zeros. You see here that this is the stack of the thread with this ID, 12A8. So we are currently debugging this thread here. Okay, so let's now proceed by entering a code that is going to be this time 20 characters long. Press enter. We stop here. Now the length is valid, so we can continue executing, and let's see now what happens. We see that we have 3 registers here pointing to the code we entered in memory. So following dump, and we have here the code, and we're going now to analyze this algorithm and see how it's going to make the validation of the data we entered. So we see that it reads the 14th byte from the beginning of the string plus 13 hex. So the 14th hex byte, which is actually the last one. and then it reads the first one. It makes an addition between these two and checks if the result is 64, which is not. It's 61 in this case. So we can start taking some notes. So we know that the first byte plus the 20th byte must equal 64 hex. So let's go on with the rest of the algorithm. Let's patch this jump to just proceed with the whole algorithm. Now we see that it reads the 19th byte to EX and the second byte to ECX, then subtracts the last byte, the 19th byte, the value of the 19th byte from the one of the second one, from the second byte, and checks if the result is 1E, which is not. So we know that the 19th byte minus the second one must equal 1E. Good. So let's proceed. Let's patch also this jump here. So we continue. Then, as you can see, it checks, it reads the 18th byte, which is 8, and XORs that byte with the third one, which is 33. So the 18th XOR the third must equal 32. So let's patch also this. Check here to continue. And then it reads, as you can see, the 17th byte, which is 7. Then reads the 4th byte, which is 4, and it does multiplication and checks if the result is equal to this here. So that multiplies and checks if the result is 26E8. So let's pass also this jump here. Let's see now what it does. It checks if the first byte is 41 hex. If you do binary edit, you see that 41 hex corresponds to A, capital. So we know that the first byte must be A capital. we also patch the jump here to continue. Then it checks if the second byte is 52 hex. We see 52 hex, the last byte is R capital. So we know that the second byte is R capital. Let's place here their values just to remember. Then it checks if the third byte is 45, E capital. So we know that the third byte must be E capital, which is 45 hex, its value. You can also binary fill with nopes if you just don't want to patch on one byte. That's up to you. Then checks if the fourth byte is 53, which is S capital. So we patch also this, and then checks if the fifth byte is equal to 2D. So we have another check here that the fifth byte must be equal to 2D. We see 2D corresponds to the dash. So the fifth character must be actually the dash character. And we see that if all the previous checks were valid, now we patch them in order to arrive at the end of the algorithm, it's going to move one in this address here to EDI, where EDI points to. And it's going to exit. To return call exit thread, let's just run. And we see now that we are back executing the main thread that was waiting for the other thread to end its execution. If you see here, the base address of the current stack is 12D and 3 zeros. You see this is a stack of the main thread. So it checks if the value in this address here, which is the one that we just saw that it was set to 1, is 0 or not. And if it's not, if it's 0, it's going to jump here and display this message, invalid password. Otherwise, it's going to continue the execution and display that valid password was entered and the access is granted. So let's now use all the information we have to create a valid password. We know what are going to be the first 5 valid characters. And we're going now to see what the rest of them should be. We know that the first plus the last one must equal 64. So the first one is 41 in hex. So we need a character that equals 23 hex. We can just type here 23 to see in which character corresponds, which is this character here. This is the last character. Then we know that the last character, the 19th character minus the second one, must equal this value here. So if we do 52 plus 1e equals 70, which is the letter P. Then we know that the 18th character XORed with 45 must equal 32. So it's the 18th XORed with the third character, which is E. So let's XOR 32 with 45 equals 77 W. And then the 17th character times this character here, S, the fourth character, must equal this number here. So we do 26EA divided with 53 equals 78, which is X. And we see that the algorithm doesn't care about the rest of the characters. So we have now 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 characters. Let's now use this code to see if it is correctly validated through the application. So it is indeed 20 characters long. The first check is valid. We see that E6 is 52, EX is 70. So it should be indeed there is a mistake here. This is should be the opposite. So it should be (52) minus this character here must equals 1e. So 34. So this should be 4. We found our mistake. So let's copy this code here and let's try to run it again through the debugger just to check that our code is okay this time. Well, making a mistake while reverse engineering an application, it's not something that should scare you. It's something that will happen very often, but this is the beauty of reverse engineering. Sometimes you have to deal with your own mistakes, but once you find them, then it really pays back. So let's see. Yes, now it's validated. Let's go for the next check. Also validated. Last check. Validated. And indeed, the first characters are the ones like ARES. We see that access was granted, the password is valid, so we managed to analyze this application. So keep in mind that through the stack you can actually realize which thread you are currently debugging by just going to the base address of the stack and then to the memory map window. You can understand, for example, the base address of this stack is this one. So the debugger says that this is the stack of the main thread. Now remember that the other thread that is implementing the anti-reversing tricks is calling the isDebugger present API. So if we set a breakpoint here, actually we need to put a breakpoint inside the loop. You see, if you now check the stack, base address is 96F and 3 zeros. So this is, we are currently debugging the thread with this ID 1BD4. And we see that now we have two threads, because the third thread is the one that checks the validity of the code of the password, and then it dies once it ends. Once the algorithm is done, it just terminates itself. So now we have two threads running. So I hope you had fun again with this video. I hope you really understood that debugging multi-threaded application, it's not always that hard, but it's really very useful to know a couple of workarounds. For example, you saw that through the stack addresses we can understand which thread we are currently debugging, because as you remembered, we have already discussed about this. Each thread has its own stack. Now, before saying goodbye, I would like to show you a couple of other tricks. For example, the first thread, the only thing it does is just checking for the presence of a debugger. the application doesn't need to wait for this thread to finish. Indeed, this thread is going to constantly run. So let's try to run this code in the same thread. For example, when we arrive here, let's run. Instead of letting the application to create a new thread to call this function here, let me just pass the application and do call and then knock this code out. So let's step in. We execute the function under the same thread now. We didn't create a new thread. We see here we have paths to bypass the tricks. And you see that this is constantly running. So if we go back from where we called this function here, we can also for example, now in this case the thread doesn't return back. So we enter in an infinite loop because this is going to constantly do this check. So it doesn't return back. But maybe here, for example, we can now patch the code and do write our own function epilogue and just return back. And now again, as you see here, it's going to create a new thread to call the function that is going to check the validity of the code. Again, we can just call this function without letting the application to create a new thread. And we don't need this anymore because a new thread is not created, so we don't need to wait. So let's just step in and enter the code, press enter. So you see that we keep executing under the same thread. It's only one thread now. Obviously I patched something that I shouldn't, so I created a memory access violation here. But I think that now you have got the point that many times, for example, especially when you analyze malware, you can just turn a multi-threaded application to a single thread. So what I'm going to do is I'm going to restart. And search for the create thread. we don't need even to enter here, just running. So we can just, for example, we know that this thread, this function executing the new thread only checks for the presence of the debugger, so we just can knock all the code. We don't need to create a new thread there. And here, this is the interesting point. This is why probably the reason why when I patched previously the thread crashed. So if you see now, we pass actually a parameter to a thread, which is the address of the variable that's going to be set to 0 or 1, depending of the result of the validation check. So if we go here, let's just go down. Just run. We see that now we know that our checks are fine, and you see that it moves to EDI. It has this value here, 12FF74. So let's try to make this a single thread application. Completely removing the code that creates both threads. So for the first one, we know that we don't care at all. We just nope this code here. But for this one, let's try to move. Let's do EDI. And just call that function. The problem is that here we need to know where this when this address is going to be retrieved. So I'm just now playing with it. You see here the value of EDI was overwritten. and this is where the value of EDI is going to be set, EBP plus 8. So let's try to do something else. We'll have our breakpoints. No, we don't. Okay, let's just patch this. And then set a breakpoint here. I will let it push 0 here. And then I will push here this address, and then call the function. Let's see if this is going to work. See that EDI has the correct just now. We don't need this. And now ESP plus 14 doesn't should point to plus 4 plus 8 C10. It should point here. This is because I messed up here with the parameters, modifying things. So just what I need to do is to rebalance. And then so let's just copy to executable all the modifications and save it as single thread. Let's just run the application now. And okay. This is where we patch the code. Let's set a breakpoint and run. The first thread that just runs the code for the anti-reversing tricks is not even started. We don't care. And then we're going to call also the function that checks for the validity of the code also in the same thread. The breakpoint here. Okay, just run. Yeah, so it's 41F40. Let's see which one was the entry point. It's 4017F0, so there was a mistake here when I passed it. It's 17F0. So we can save this change. Okay, so now we enter. Let's just paste the password, keep checking. We bypass all the checks, everything is fine. We return back, we rebalance from the two parameters, and then it checks if this value is 1, which it is 1 because the code was validated, and just run. So you see that we turned the application into single thread. With no problems at all. The difference was that the second thread, the second function that was running to a new thread, was also accepting a pointer to that address here, where it stores 0 or 1, depending on the result of validation of the code validation algorithm. So I hope you had some fun. I recommend that you spend some more time playing with this application.